Apologies for the little back and forth. And I'm going to share my screen with Alvin there one more time. Okay. All right. So a few preliminaries. We'll be talking about the some COVID-19, the officers, and there is an officer election ongoing now. I'll mention that. There's also the IMS symposium coming up. I'll mention a couple of things on there, and then we'll go ahead and introduce Alvin and his talk. So a few things to note. This meeting is being recorded and is being broadcast live on Zoom. Links to the recorded video and slides will be sent to all registrants. Please keep your cameras off and microphones muted. And we ask that you pose your questions by using the raise hand reaction button of feature of Zoom. We will unmute you to ask the question. Alvin, if I might ask, are you okay with doing breaks within your talk at maybe 15, 20 minutes to allow
sure.
for some questions at that time?
So I've got a slide in the middle for an intermission for Q&A.
Oh, that'd be perfect.
It's a pretty long presentation, so I figured it'd be good to give people a chance to take a breather.
Well, and we find that if you can catch folks who might not be following some concept early on, that can make the latter part of the talk much better if some of those questions are answered. So we really appreciate that. Ask that your Zoom display name matches the one you used to register. This will help us to check in your attendance, which is quite important for the chapter. The COVID-19 pandemic is still with us, and all-person meetings related to our chapter are canceled. Our monthly technical meetings and officer meetings will continue in online webinar format only until further notice. The 2021 chapter officers for the Santa Clara Valley, San Francisco chapter of MTT Society of the IEEE are Utkarsh Krishna, myself, Tom McCann, the vice chair, Venkata Gade is the secretary, and Tan Q is the treasurer. The Institute of Electrical and Electronics Engineers advances technology for humanity by inspiring a global community through highly cited publications, conferences, technology standards, and professional and educational activities. And the Microwave Theory and Technique Society within the IEEE focuses on the theory and applications of radio frequency guided and wireless wave technologies. Support us by becoming a member. You can join the IEEE at IEEE.org, and you can join the MTT Society at MTT.org. You can also, if you're a member, you have the privilege of voting for officers, and this is the way to make a vibrant chapter. So please vote. You have until midnight East Coast time, November 22nd. So I guess that would be like 9 p.m. November 22nd Pacific time. The IMS is a tremendous conference. If you've not been, I highly recommend you consider it. Next year, we anticipate being in person in Denver. New for 2022 will be something of interest to industrial authors. Industrial authors will be given the opportunity to engage with their audience with impact via live demonstration. So this is where the authors can share their papers and, interactively with the attendees. And this is a quite highly technical, really great way to communicate your concepts. To qualify, submit your paper on or before December 7th at ims-IEEE.org. We're really lucky, I think, to have Dr. Alvin Loke come to speak with us about nanoscale FinFET technology for circuit designers. This is a very relevant topic to the Microwave Theory and Technique Society, as many wireless transceivers are made with FinFETs, and they're they're kind of difficult, I'd say, at the smallest node, as they're less common, and so really we need folks like Alvin who can help teach how to get better at understanding FinFET technology for circuit design, sort of analog circuit design, and so we're really glad to have him here. Alvin recently joined NXP Semiconductors as a technical director in San Diego, having worked on CMOS spanning 250 nanometer to 2 nanometer at Agilent, AMD, Qualcomm, and TSMC. He received a Bachelor of Arts in Sciences degree with highest honors from the University of British Columbia and the MS and PhD degrees from Stanford University. Upon graduating, he spent several years in CMOS process integration, but since 2001, he's worked on analog mixed signal design, focusing on a variety of wireline, links, and design model technology interfaces and analog design methodologies. He's been an active IEEE Solid State Circuit Society volunteer since 2003, having served as distinguished lecturer, Custom Integrated Circuits Conference committee member, webinar chair of Denver and San Diego chapter chairs, and guest editor for the Journal of Solid State Circuits and Solid State Circuits Letters. He currently serves in the Solid State Circuits Society's Administrative Committee and VLSI Symposium Committees, and as Solid State Circuits Society chapter chair and San Diego Joint MTT-S chapter vice chair. Alvin has authored over 60 publications, including the CICC 2018 Best Paper, Invited ISSCC Paper, the VLSI Symposium, the BCI-CTS Short Courses, and the ICI-CDT Keynote, and holds 29 patents. Now, CMOS scaling remains and maintains economic relevance with 5 nanometer SoCs already available in consumer products for a year now. With 3 nanometer deep in product development, most feature size reduction and design technology innovations co-optimized for logic and SRAM scaling continue to offer compelling node-to-node power, performance, area, and cost benefits. In this tutorial, Alvin will start with a brief history of transistor evolution to motivate the migration from planar to fully depleted FinFET, and he will summarize the key process technology elements that have enabled the FinFET CMOS nodes, highlighting the resulting device technology characteristics and challenges impacting design. To address the growing effort for physical design closure, we'll cover the design strategies, including density-friendly layout, continuous active area layout, and template-based analog cells. He'll conclude with a discussion of what remains in FinFET development and a peek at transistor architectures on the horizon. Alvin?
Hey. Okay, so I guess I should share my screen now?
You should share your screen again.
Okay. Can you guys see this okay?
Yes.
Awesome.
Very good.
Okay. Well, may I take it away?
Please take it away, Alvin.
Okay, thanks, Tom. Hey, everyone, thanks so much for spending the next probably hour and a half to 2 hours to listen to this talk. Oops, what's happening? Uh-oh. Okay, yeah. So, anyways, appreciate the kind introduction. Really appreciate the opportunity to speak at the MTT Santa Clara Valley chapter. I was going to say I also am very involved in arranging IEEE presentations and know how much work it takes to do this community service for everyone, and just really appreciate the opportunity. I see some familiar faces of folks who I know, and appreciate your moral support, as I know you've probably heard this presentation or a similar presentation in the past. So this is this device tutorial is largely an encore of a short course that I gave at several conferences, including ISSCC. And so my hope here is to not necessarily give you specifics about numbers, but more importantly, hopefully impart some understanding into the device physics and also the technology and what FinFET technology is bringing us. Okay, so just as a start, I want to make sure I acknowledge my friends and former colleagues at Qualcomm and TSMC who had a important part in one way or another in contributing to the material that I'm about to cover. Okay, so any talk on transistor scaling or so forth has got to start with some intro slides on semiconductor demand. And as you can clearly see, as we've evolved over time, it's really been different forms of computing that has driven semiconductor demand. Okay, and it literally has been soaring beyond expectation. Of course, we started, back in the essentially in the late 60s, early 70s with mainframe computing, and then mainframe computing evolved to personal computing, which then came back to a mainframe 2.0, which is called cloud computing. But at the time when this happened, mobile computing started taking off, and pretty much these days, we're in an era of ubiquitous computing where pretty much anything with a power switch will have some silicon content in it. And as we know, where we are now, 5 nanometer is now in products. The A14 chip was made available by Apple a year ago. They're TSMC's lead customer. And so more and more companies are hopping on the 5 nanometer bandwagon, including NXP Semiconductors, which is where I work, but more targeting not edge computing as well as auto applications. So what makes this all happen? Obviously, the much celebrated Moore's law. Moore's law is essentially the result of economics, right? It's just a very, very concise way of essentially saying that when you make things smaller, it makes things cheaper, which is just an absolute thing of beauty, right? This has happened through the course of several eras of technology scaling, where for 3 decades, we've enjoyed what's referred to as classic Dennard scaling, okay? And that lasted from 10 micron down to about 130 nanometer. When that ran out of gas, we started introducing mechanical strain and HighK metal gate into our transistors. And that was able to squeeze a few more nodes from 90 down to about 32 nanometers. And about 9 years ago, Intel introduced the FinFET architecture at 22 nanometers. And basically, this train has been going on for multiple generations now, where you've got the FinFET transistor architecture, as well as extensive design technology co-optimization to basically make these processes cost compelling and worth pumping in literally hundreds of millions of dollars to develop chips. So what we'll do in this talk is we'll cover the evolution of how we got to the FinFET. We'll cover technology scaling enablers that made the FinFET possible, FinFET nodes possible. It's not just FinFETs that matter. It's all the other stuff around the FinFET that actually makes the scaling story compelling. Okay, we'll cover design realities. That's a little bit of a gripe session, and then talk about some of the design strategies to deal with it and mitigate these design realities. Talk a little bit about what's ahead on the horizon, and then we'll wrap up with some conclusions. Okay, so covering the evolution to FinFET, we'll talk about Dennard scaling, how we are extending Dennard scaling with mechanical strain and HighK metal gate, as well as migrating finally to the fully depleted device, which a FinFET is a subset. Okay, so when we talk about scaling, we cannot avoid talking about short channel effects, because when things get smaller, right, usually non-idealities and different challenges pop up. So when we're trying to scale our transistors, okay, one of the inevitable things we need to do is to reduce what's referred to as the CGP, the contacted gate pitch, Okay, historically it's been called the contacted poly pitch, but the gates today are no longer made of polysilicon. So I'm being proper by using the word gate. And so we want to reduce this contacted gate pitch in order to scale the area of the transistor. And this will inevitably reduce the gate length. Okay. Now, the problem is when you reduce the gate length, right, it actually weakens the gate control of the channel depletion underneath, due to body depletion and as the channel forms. And that's, simply the result of the source drain to body junction depletion regions eating up a significant percentage of the shadow of depleted region or depletion region underneath the gate. And so one of the natural consequences of shrinking the gate length in light of this source drain junction is the VT rolling off. Okay, that's a classic VT short channel effect. Okay. Now another manifestation of short channel effect is what happens when you increase the drain voltage. When you increase the drain voltage, the reverse bias of the drain to body junction thickens the depletion region or widens the depletion region, which in turn eats up more into this red box here, and therefore making the gate lose even more control. And when you increase the gate, the drain voltage, the VT also drops. This is just a manifestation of what's commonly called drain-induced barrier lowering, or DIBBLE. Okay, so the blueprint that the industry has followed for about 3 decades has been the Dennard scaling recipe. And so the idea is that when you have a device that's of this size and you want to scale it by some linear dimension alpha, okay, the first thing you do is you want to reduce the gate length, okay, but reducing the gate length comes with it several consequences you have to address. So one thing you obviously need to do to reduce short channel effects is to reduce the thickness of the depletion regions, which requires the doping concentration to go up. Okay, and when the doping concentration goes up, right, that will invariably cause the threshold voltage to drop, or sorry, to increase. Okay, which necessitates that the oxide thickness gets less and less to recover more gate control of the channel charge, and therefore bring your VT down from being unacceptably high. And when you've got thinner gate oxides, naturally electric fields go up, which requires you to reduce the voltage in order to prevent device breakdown. So this recipe has worked very well for about 3 decades. And the net result was about 2 orders of magnitude reduction in the gate length and the oxide control, oxide thickness. But it hasn't been completely quite so linear. There has been several key innovations to extend short channel control. The notable one is that the channel profile in the transistor, both horizontally and vertically, is non-uniform. Okay, and so the textbooks where we basically see uniformly doped bodies, that's obviously a big lie. Generally what you do is you have to optimize the body doping profile by using these lateral halo implants that are high tilt, high angle implants that get just underneath the edge of the device here. And the idea is that you want to basically increase the doping concentration to make the depletion regions thinner so that you can recover some short channel control. You also have a vertically retrograded well. And with this structure, we have these spacers to enable basically a source drain extension region to form. And so the idea here is, with this resulting halo device structure with source drain extension implants, we have depletion regions that are thin and narrow that basically allows us to have good short channel control. But then we basically need to, compromise, not have the series resistance of the transistors, access resistance being too large. Otherwise, you get significant short source degeneration. And by having the spacers self-aligning the source drain contact regions with a much thicker and deeper source drain region to have lower source drain resistance or diffusion resistance, allows you to recover some device performance. Okay, so what are some of the obstacles to continuing this this recipe? as I mentioned earlier, we're using higher body doping to make the depletion regions thinner. And so this naturally will increase dopant scattering. So ionized impurity dopant scattering is going to cause the channel mobility to go down, which is not good because you get less current. Okay. Also, the gate dielectric being thinner, you reach a point where basically electrons can just teleport from gate to the channel, and this severe tunneling leakage results in severe gate leakage. Okay. We also have, as we thin down the dielectric, we run into an issue where we've got, the finite conductivity, I'm sorry, of the polysilicon leads rise to poly depletion, which means that the charge on the gate is not going to be infinitesimally close to the gate oxide interface on the gate side. And so the charge centroid on the gate gets pushed out away from the interface. Furthermore, the increased doping concentration causes these quantum confinement effects. I think of quantum confinement effect as basically going back to particle in the box problem. When you've got a potential well that's very, very narrow, what it leads to is quantization of energy levels inside this quantum well. And it's really no different here. We've got a little bit of a triangular quantum well as opposed to a square quantum well, but the idea is pretty much the same. Okay. The net result is, because of the quantization of energy levels, as well as restrictions due to energy state density of states, restricting the number of electrons you can populate at these lower level quantum states, electrons cannot be infinitesimally close to the silicon surface side of the gate oxide, which means that the charge gets pushed out further away from the interface. So the net result is you essentially can think of charge on the gate being physically separated from charge in the channel by essentially three capacitors in series, which obviously is a lot less than the capacitance of one device of just the gate oxide itself. Okay, and so you have less gate control. Okay, so what have we done to fix that? We have introduced channel strain, and as well as HighK, or high permittivity gate dielectric and metal gate. So what are these? What do these innovations look like? So from a mechanical strain perspective, what we're doing here is we are physically exploiting silicon's piezoresistivity, which means that the electrical properties of silicon depends on its mechanical strain state, whether it's in tension or compression. Okay, so silicon is extremely piezoresistive. Basically, what seems like this ceramic block of material, which has very, very, which looks very stiff and brittle, it turns out that if you can basically have 1% induce 1% channel strain in the lattice, you can actually increase the mobility, or another way of saying, reduce the effective mass of the carriers by several times, which directly translates to several times increase in current. Okay. Now, unfortunately, because silicon is this brittle like ceramic kind of material, it has a very high Young's modulus, which means that you need to have extremely high stresses, okay, in the order of several gigapascals, stress it with gigapascal materials around in order to get that 1% channel strain. And just as a reference, steel will yield at about 3/4 of a gigapascals, and we are routinely straining our transistors at several times that, just to kind of give you an idea. Okay. Now, the NMOS and PMOS transistors, they do want opposite stresses along the gate length direction. And to further complicate things, this stress is actually very anisotropic, which means you want different stress polarities in different directions. Okay. Now, one thing to note about mechanical strain techniques is that it works only for short channel transistors, not effective for long channel. And that's very simple to visualize, because you've got these source strain regions, typically they're under a lot of stress, and you've got a volume of silicon that's sandwiched in between that you're trying to compress or stretch, okay? So the longer the channel you have, the more volume of silicon you have to resist the surrounding pressure that's being exerted onto the transistor channel. Okay, and this is not good for analog transistors, because we typically need long channel devices for high output resistance. And so there are a host of different techniques that are used. for employing or incorporating mechanical strain in the transistors. Okay, the other technique that's used is a HighK gate dielectric and metal gate. And so the idea here is that we want to essentially extend the COX scaling, okay, try to make COX larger and larger. And one way of doing that is to replace the oxide, gate oxide, nitrided gate oxide material with a hafnium oxide HighK dielectric material, which has a much higher permittivity, which means that for the same COX, you can make it a lot thicker. Okay, and so having that thicker gate oxide gives you less gate current leakage or gate leakage current. Okay, now in conjunction with that, to solve or reduce the gate depletion issues with polysilicon depletion, the HighK gate dielectric is actually mated to a conductive metal gate work function layer. Okay, so what you can see here is that we've got the HighK material in gray, but then we basically deposit this work function layer, which is going to be different. It's going to have a different material property for to replace N+ poly and P+ poly respectively. Okay, because we're trying to go after a material with a work function that lines up with the conduction band edge in the silicon band structure for N+ poly, and conversely lining up to the valence band edge for P+ poly. Okay, and when HighK metal gate was first introduced at 45 nanometers, basically the different VT flavors for a given polarity were being tuned using body doping or implants. HighK metal gate technology is a headache to integrate. There are lots of integration challenges you have to deal with. For one, the industry had to adopt what's referred to as a replacement metal gate technology, such that you have a stable VT. The reason is the HighK metal gate interface is thermally unstable. And if you were to expose the HighK metal gate interface to the high temperature source strain anneals that you need to activate the dopants after implant, that can cause the VTs to shift dramatically in your transistors. And in fact, I've seen, for instance, PMOS VTs as high as 0.7, 0.8 volts, which would render the technology useless. Okay, and to further complicate things, one other key process integration step that was required to make this happen, HighK metal gate technology happen, is to move the silicide module. Historically, the silicide module happens before you deposit the contact dielectric, but then with the replacement metal gate integration happening after the contact dielectric's deposited, typically there's a post-deposition anneal that you need to have for making your HighK dielectric more reliable for TDDB, time-dependent dielectric breakdown concerns. That high temperature causes the silicide to actually disintegrate if you introduce it too early. And so to deal with this, the silicide's actually built, deposited at the bottom of the trench contact once the diffusion contacts are formed. Okay, so that lasted for several generations, and it was clear that even moving into 32 nanometers, we were running into an issue where a lot of these transistors were becoming more and more difficult to scale because the transistor was having a difficult time to shut off. Okay, how can we view that? Well, you can think of a transistor in subthreshold essentially as a bipolar transistor. Okay, where the surface potential or the base of the in a bipolar is now analogous to the surface potential of the transistor near the source of the device, is really controlled by a tug of war between COX, which is what you want to control, but it's got this parasitic body and drain coupling that basically prevents the gate voltage from tightly coupling the surface potential up to the gate. Okay, and so what that means is that, as you've seen, when we try to scale to smaller and smaller gate lengths, shorter and shorter gate lengths, what essentially has happened is body dopings have gotten higher and higher, which has made the the charge separation, depletion region is thinner, which means that the body coupling and the drain coupling becomes stronger, which works against you. Okay, and so when you've got this happening, you've got a capacitor divider, which basically works against you. You really want CB and CD to be zero. You want COX to be fully controlled, tightly couple the gate to the surface potential. And so the net result is you're going to get a higher subthreshold swing, which means you need more change in gate voltage to induce several decades of transistors. In other words, of transistor current. And so when we're trying to scale the supply for lower power, we're trying to scale the VT, okay, obviously this higher subthreshold swing is not working in our favor. And so if you want to have high performance with conventional Dinard-based devices, even with mechanical strain and high-K metal gate, it comes with a penalty of high leakage. So this is when we started migrating to fully depleted devices, okay? So a word before we get into fully depleted devices, let's go back to transistor basics, okay? So what is a field effect transistor? Well, basically realize that in a normal transistor, what we basically have body dopants for is to mirror gate charge. When we apply gate charge, okay, we induce ionized dopants in the body, which in turn sets up dipoles, which causes electric fields to flow vertically through the gate oxide and into the surface of the transistor, which then induces surface inversion and allow us to short circuit the back-to-back diodes between source and drain. Okay. Now, one thing I want to highlight here is that although in our device textbooks, it always starts by basically saying, okay, well, the MOSFET is formed by having, a body of, having uniform doping or whatever, having dopants throughout this transistor surface. The key here is, I want to just highlight here, is that surface dopants are not fundamental to field effect action. What is fundamental is setting up dipoles to create electric fields, which then causes surface inversion. What you can do is if you can somehow move the dopants away from the surface, creating a region here where you have no dopants, okay, you can still have, and essentially you have a very retrograded well, you can still have this dipole set up this way, okay? And there are some benefits in doing this. When you have the so-called fully depleted undoped surface, because you have no dopants right at the surface, okay, you have a lot of goodness. One goodness is that because you don't have dopants, or you have very minimal dopants along the surface, you have a lot less channel scattering, which means that your mobility gets better, okay? Furthermore, because you don't have field lines terminating inside here because you have no charge, the drain charge will terminate downwards deep into the body, which means that the drain charge has very little control over this channel you're trying, or this depletion region you're trying to control with the gate, which means that drain-induced barrier lowering actually gets lower, which is a thing of goodness. And by doing this, we've essentially built a geometry-based versus a dopant-based device, very much like a parallel plate capacitor, where it just turns out that the parallel plate capacitor dielectric in between is really a layer of silicon where we have a channel where electrons travel, as well as the gate oxide. There are multiple ways of implementing a fully depleted device. You can build planar on bulk, which is what's drawn here, but it's actually very difficult to do, because to do planar on bulk requires you to epitaxially grow an undoped region of silicon on top of a heavily doped region of silicon. And that's very difficult to do because epitaxy is a very high temperature step during which the fast diffusion of dopants from underneath will rush upwards to basically dope the undoped layer that you're trying to keep undoped. So it's generally very difficult. You can have planar on SOI, which is FD-SOI. Sometimes it's called extremely thin SOI or ultra thin body and box SOI, where the idea is that this layer here, this fully depleted undoped surface, you replace that with a sandwich stack of an SOI layer, followed by a buried oxide layer underneath. And so just fundamentally, the substrate is much easier to create a fully depleted layer, undoped layer compared to planar on bulk. You can also have 3D on bulk, which is essentially a FinFET, or you can have essentially FinFETs on, say, SOI. Turns out that you don't need this, and so the industry has stayed with 3D on bulk. Okay, so what does a fully depleted device offer you? Well, by basically having the dopants being a lot less, you can basically have market reduction in the body and the drain capacitance, which means that this tug of war is now strongly favoring the COX. And so what that means is that every millivolt of gate voltage change you have will then have a much larger percentage of that millivolt show up as a change in the surface potential. The net result is you need less gate voltage to basically change the subthreshold current by, say, three orders of magnitude, for instance. And what that means is that the subthreshold slope gets steeper. The dibble, which is a measure of the separation between the saturation and linear threshold voltages, is tighter. The body effect essentially is now going away, because with the body coupling being very weak, essentially applying a body voltage will have very minimal impact on the surface potential, and therefore the body effect essentially disappears or near disappears in a FinFET node or a fully depleted device. Okay, one of the beauties of this is it's perfect for accommodating the mobile era, in the sense that when we've got a much steeper subthreshold swing, okay, you can basically get much lower power, or you can have your VT and your supply voltage go way down, okay, for the same off current and the same on current. And so you're basically achieving the same performance, same leakage for lower power, okay? And that's just a fundamentally superior architecture is giving you these benefits, okay? So, and just to kind of put some numbers here, let me just give you an idea. For instance, in TSMC 20 nanometers, it's not uncommon to see, for instance, subthreshold swings in the order of about 120 millivolt per decade. And so if you've got, for instance, 3 orders of magnitude of current separation, 1000x between on and off states, say, what that means is 3 decades requires a minimum threshold voltage of 3 decades times 120 millivolts, or a threshold voltage of 360 millivolts minimum, in order to achieve that separation in on and off current. In contrast, if you can basically make the subthreshold slope ideal or near the ideal value of 60 millivolts per decade, let's just say 65 millivolts per decade, 3 decades times 65 millivolts per decade is going to give you 195. And so 195 millivolts is 160 millivolts below 360. So for the same performance, same leakage, with a much steeper subthreshold swing, you can basically reduce your your supply voltage by 165 millivolts with essentially no degradation in performance and leakage. So that's the beauty of what FinFET offers, or fully depleted devices offer. Okay. Now, one of the perhaps less intuitive things about FinFET is not only, so with less dibble, basically you're going to get a device that has much less drain voltage dependence, which means that the R out of the transistor is going to be better. And this is good for analog, but what's perhaps a little bit less intuitive is actually also better for digital. And given that in our world, we essentially, if you're working in analog, mixed signal, or RF, we're essentially the third-class citizens enslaved to what the digital and the memory guys want, okay? But if you can basically come up with a technology which benefits digital, the cell becomes very simple, because they're the driving force behind the technology development. So if you, for instance, take a simple inverter, and you transition the simple inverter where the input is low, and you transition it, the input to high, making the output go down, this would be kind of the locus of where the inverter switching trajectory, what the inverter switching trajectory will look like as it's going from state 1 to state 2 to state 3. And as you can see here, if you were to use ID-SAT, which is this upper right corner of the IV curve, it's going to grossly underestimate the CV over I switching delay because the current's grossly overestimated. What IBM did was to use a new metric known as the effective current. And the effective drive current is the average of two currents. Basically, one is I low, which is the drain current when the gate is at half the supply, but the drain is at full supply. And the other value is I high, where you have now the gate voltage at full supply and the drain at half supply. This metric is important to realize that if you have a device with no dibble, okay, you can get an increase for the same I low, a much higher I high, which in turn increases your I effective when you have much less dibble. And so this is a kind of a nice way to illustrate that when you have less dibble with a higher effective current, not only does your R out get better, but your transistors also, or your logic gates also switch faster. Okay, so let's cover now technology scaling enablers. I'm going to cover FinFET, but FinFET isn't the whole story. Also cover lithography, self-aligned patterning, mechanical stressors, and HighK metal gate as applied to FinFET. Also, we'll talk a little bit about the middle end of line and self-aligned contacts, as well as some other design technology co-optimization that has taken place. Okay, so as we move from planar to FinFET, what we're effectively doing is, I think of it as tectonic plates that smash into each other and creating mountain ranges. Okay, and kind of like Mount Everest getting higher and higher by inches each year. If you have a gate that's on top of the tectonic plate, as the tectonic plate rises up and up, well, the gate's going to wrap around this rising mountain range. And that's how I visualize this. And so basically, you're just taking active region for their transistor as well as for your tie, and you're effectively finifying it, so to speak. Okay, and you can do this for NMOS and PMOS also. And here I'm deliberately showing that there is a P-well, because quite often designers forget that even though you don't draw a P-well, there is intrinsically a P-well that's drawn there. It just happens to be the complement of the N-well layer. What are some of the properties of a fully depleted FinFET? So the obvious one is, as we're now having a transistor where the channel, a cross section of the channel, it's no longer like a simple width like this. It's now an upside down shaped U. Okay, and one clear benefit is basically performance for a given density. So in a given area, you're going to get substantially more on current and GM. Okay, simply because the effective width, which is basically the perimeter, or not quite perimeter, but basically twice the height of the active device fin and the width of the fin. When you actually look at modern day transistors down to 5 nanometers, they're actually closer to 4 times the fin pitch. Okay, so what would have been normally your channel width on a planar scale, by wrapping things into the third dimension or protruding things into the third dimension, you're actually getting 3 to 4 times effective gate area, or gate length. Gate width. I'm sorry. Okay, and so this quantized, the channel width is quantized in quanta chunks of the number of fins you're using. This can be a challenge with SRAM and logic, because, for instance, for SRAM, we are trying to finesse the, say in a 6 transistor SRAM, we're trying to finesse the relative drive strengths of the pull up, pull down, and the access pass gate transistor to basically make the cell readable and writable. Because we don't have much in terms of choice in channel width, basically a host of plethora of different read, write, bit line assist techniques, etc., have become very popular, such that you're using the voltage overdrive as the analog knob in order to fine tune the conditions you need to establish readability and writability, which are often orthogonal to one another. Okay, in FinFET for analog, it's not a particularly big issue to have these quantized channel widths, largely because the GM per fin is pretty small. It's in the order of 10 to 100 micro Siemens. Okay, and we're typically going after conventionally in the order of 1 millisiemen type numbers for typical analog circuits, you need many fins to accomplish that. So the quantization of the channel width is really not as big of a problem in analog. I'd mentioned lower dibble, which means that you have higher R out and intrinsic gain for a given channel length. Now, there is a caveat, because this technology with HighK metal gate, replacement metal gate technology, has caused market reduction in the allowable maximum channel length. And so although for a short channel length, you get better intrinsic gain, you're losing out in not having a very long channel lengths anymore, okay? The body effect in this technology is very negligible, which is no surprise. You can pretty much check out all your body biasing techniques, because your threshold voltage will shift no more than 5 to 10 millivolts across a body bias of supply. Okay, the mismatch is less in these devices because we're not really counting on doping or implants. We are less prone to random dopant fluctuation, but then we still see geometry being very heavily dependent on area and geometry. Okay, parasitics is what we have unfortunately picked up by having the structure being very, very tight together. Basically, with a tight three-dimensional structure, the source drain resistance is very high, meaning that the source degeneration is a serious problem, and the coupling of the contacts to the gate, the source drain to the gate, is also very high. One other thing to note is that the fin width here is much less than the fin pitch. Typically, they're about 20 to 25% of the fin pitch, which means that although the junction capacitance facing downwards is a lot less because you have a lot less area, your well resistance is also a lot higher. And as we'll see later, this has significant implications on things like latch up, where you need very low well access resistance to mitigate. The 1/F noise in a FinFET is comparable to much worse. Realistically, it's actually much worse. When you're packing a lot more current flowing in a much smaller area, naturally, you're going to deal with more reliability concerns due to self-heating. Okay, so just looking a little bit at an analog mixed signal dashboard, for a planar device going to a FinFET, you can see that we are definitely reducing, going from 28 to 16, definitely reducing in supply, and also the threshold voltage has gone down, where the leakage has gone down substantially also. So this is like all goodness. The on resistance has gotten better. You get better switches. You have better intrinsic gain, as I mentioned, due to reduced dibble and also more mechanical strain. You've got better mismatch with less random dopant fluctuation. And you can do this all in lower and smaller area, of course, in a more expensive process. So from a power performance area story, this is all goodness if you stick with only FETs, okay? But I'm an analog mixed signal designer, what I've learned is, over the years with FinFET, is that these scaling benefits really are not that applicable to analog mixed signal, quite like to digital. And furthermore, as you can see here, the scaling benefits going to say 7 nanometers has actually started saturating more and more. Okay, so let's talk about some of these technology enablers here. So foundry pitch scaling obviously has been key. You can't talk about scaling without lithography. But if you look at, for instance, how the minimum pitch center to center separation between two features has been scaling with age, or with through the years with technology node, you can see that the technology physical scaling factor has been less than the what we've enjoyed historically to be about 0.7x per 2 years, or on an area, it would be 0.7 squared, or about half per 2 years, okay? And so the physical scaling has actually been getting increasingly incremental over the years. The node name basically means nothing these days, okay? It is a marketing number that's no longer tied to the gate length. It is essentially name that's somewhat loosely tied to area scaling, and it's one of those marketing things that is making more and more difficult to compare different process nodes. Extreme ultraviolet, which has a wavelength of 13.5 nanometer, did get introduced only at 7 nanometers, and in 6 and 5 nanometers and onwards, it's obviously just commonplace now. Okay, but before then, before 7 was introduced, basically we were stuck with using a 193 nanometer wet immersion lithography, which has a single exposure pitch limit of about 80 nanometers. And so when we needed to basically go below the single exposure limit, the industry had adopted a host of different process complexity and cost to get these features. Okay, how will we do that? So some of these lithography innovations are shown here. One is pitch splitting. The idea with pitch splitting is you would interleave 2 or more exposures, okay, to print a given layer. Obviously you would print essentially alternating features with one mask, and then every other alternating features with the other mask. Now, when you're doing this with different masks, you're obviously going to be prone to overlay or misalignment between these masks. So if you misalign, for instance, mask A and B in the X direction, you could inadvertently end up with a space that's too tight and cause shorts in the desired feature. Another thing you can do, which is done to reduce end spacing, is the use of extra mask for orthogonal cuts. Okay, and so here the idea is that if you were to basically have features that ended because of near field diffraction effects, you would get a lot of rounding and corner pullback. But then if you basically pattern a bunch of horizontal lines and with another cut mask, you basically expose the breaks, you actually get much cleaner features here. And the idea here is that you may get near field rounding diffraction effects at the ends of your cut mask patterns, but then because they're not part of the original features you're trying to slice through, you don't care. Okay, so this technique is used quite extensively. In fact, it's used so extensively in these techniques, lithography techniques, is that quite often the cut masks are also pitch split because the features, the pitch of the cuts themselves are so tight. But once again, with this particular technique, just like pitch splitting, lithography overlay is a limitation. If, for instance, you imagine this cut pattern being misaligned in the Y direction, you can clearly see it's going to pinch off this pattern here at the bottom. Okay, so as you might expect, the industry has been working towards self-aligned approaches, which are essentially insensitive to misalignment. This is the way fins are patterned. Short channel gates, middle end of line, lower back end of line, they're all patterned this way. So the idea here is you want to basically pattern a sea of spacers, which you then use as a hard mask for basically patterning your underlying layer. So the way you do this is you start by patterning using your 193 immersion lithography approach, a sacrificial mandrel, which you basically then do a spacer process, and you grow these spacers on the sidewall of your mandrel. You then remove your mandrel, leaving twice as many spacers as you had mandrel, okay, but at half the pitch. And then you basically go to proceed to use the hard mask, spacer hard mask, as a pattern for etching the underlying material. Okay, now there's a limitation to this single self-aligned double patterning approach, as it's sometimes referred. The problem is if your pitch limit here is say 80 nanometers, you can't have a pitch looser or tighter than 40 nanometers. Here we are way past the point of fin pitches that are less than 40 nanometers. So in order to get those even finer fin pitches, we repeat this madness again, where basically we use our spacer ones as the mandrel for growing a set of spacer twos around. So now you have twice as many spacer twos as spacer one, or 4 times as many spacer twos as your original mandrel. And so now you're getting 4 times as many fins as you have mandrel. And so this technique would be used to basically get you down to the sub 30 nanometer or actually sub 40 nanometer fin pitch. One of the side benefits of using this spacer-based approach is because the spacer deposition being conformal, it means that your line edge roughness for each hard mask feature or for each spacer is correlated between left and right edge, which results in less width variation. Okay, there are some variations of spacer-based patterning. One is to use a spacer trim mask. So the idea is if you want to basically get another feature width, let's say you want to produce, say, an L-min and L-min plus some delta gate length, what you would do is you would pattern essentially a sea of L-min plus delta gates, and then use a trim mask, and in a blanket etch, essentially trim away the width of the exposed features by delta, and then now you have two different fin widths, or sorry, gate widths, which you then, or gate lengths, I'm sorry, which you then can pattern different gate lengths. Okay, that's one thing you can do. Another is you can use spacer-based patterning in conjunction with block masks. Okay, and so the idea is if you actually have, although you may have one single spacer width, but by using mandrels of different widths and that are spaced apart differently, and using a block mask to basically bridge between several spacers, you can then have more combinations of feature spaces. Okay, a quick word about extreme ultraviolet. It was introduced in 7 nanometer production. So with any lithography technology, the key challenge is—
Alvin?
Yeah.
I was wondering, I'm wondering if it's, before we go into EUV here, if we want to take a few questions, or
Sure, yeah.
Or if you want to, let's just see if there's any questions.
Sure.
If you have a question,
let me finish
please,
lithography, Tom.
okay.
On lithography, and then we've wrapped up this one section. Okay. So with EUV, basically, like I say, you need to harvest a lot of photons, which is a very tough thing to do. And you need to make sure that every photon maximizes its impact on the resist that it's trying to expose. Okay, with 13.5 nanometer wavelength, basically, at such high energy, with such high energy photons, everything becomes absorptive at these wavelengths, which means that your masks are no longer refractive; they now become reflective. So the optics of the mask, and how you do all the projection optics is all reflective. With EUV, basically what TSMC has done is EUV has essentially, companies like TSMC has essentially used EUV to essentially simplify their process. Okay, what would have been done with multiple, as many as 5, 6, 193 immersion masks, where you've got different pitch splits, you've got cut masks that are even pitch split and block masks. You can collapse that all to a single EUV mask, and basically you get better process simplicity because you're using a shorter wavelength. Your OPC is easier, your DRC is easier. You get better overlay because you have fewer layers you're trying to align. And the idea here is faster cycle time and cost saving. Okay, so yeah, let's take some questions now.
Okay, we have one question. Bertson,
yeah. So I was curious. You were before you went into the FinFETs. You said one of the ideas was to have a undoped sort of channel right under the gate. How does having this 3D fins help you create those undoped layers? Because the well is still doped, I presume.
Well, so the doping concentration. Okay, so let me step back. Oops, give me a second. Let me step back to show the picture of the FinFET. And okay, so here we have a picture of FinFET. Okay, so we start with conventional low dope substrates typically, right? I mean, typically substrates have doping concentrations about 10 to the 15 dopants per cubic centimeter, or 20 ohm centimeter type substrates. The way we would build the FinFET, we would want to leave the fin portion of the fin where the gate wraps around as undoped as possible. But the region underneath the fin, or underneath where the gate wraps around, the portion of the fin that's underneath, okay, and that's kind of like, below the iceberg, so to speak, the surface of the iceberg, you want that to be very heavily doped, okay? And so there will be implants, what's referred to as sometimes anti-punch-through implants, that are done to dope the region heavily underneath the fully depleted portion of the fin at the surface. And you need to heavily dope it such that you don't have subsurface punch through, where you have depletion regions from the source and drain to the body or to the well, essentially shorting through each other underneath the fully depleted region where the gate wraps around. Okay, Burson, I'm not sure if that answers your question.
Yeah, yes, I think so. So the doping goes under the source and drain, but I guess this cross section from the top that comes under the channel doesn't get doped.
Yeah,
but at least not as much.
That's right. So you want the portion that is like the light yellow, okay, and the light yellow also extends underneath the gate. You want all that to be heavily doped,
okay.
But you don't want the top of the fin to be heavily doped, because you want it to be fully depleted to get all the benefits of fully depleted, like less carrier mobility, scattering, all those things, right? Yeah.
Okay, thank you.
Okay. Any other questions right now, or we can ask Alvin to move on?
Tom, I have one request to the attendees. Please make sure your name is reflected as you have registered. This will help us check you in. You can rename yourself by clicking, on the more, there is a rename option. For some of them, I see ASAC. Can you please rename yourself on the chat windows? Thank you so much. Thank you, Tom.
Thank you, Venkata. Yeah, so please do change your name as your shown name here. If you can, then please make it what you use to register. All right, we'll go on now with mechanical stressors and FinFET.
Okay. So anyways, mechanical stressors, the usage of it has actually carried over as we entered the FinFET era. Same basic idea. You want tensile stress in NMOS, compressive stress for PMOS. Okay, but it's quite a bit more complicated because you've got a three-dimensional channel now. You've got a sidewall, which is 100 normal, and a top of the fin, which is 110 on the sidewall and 100 at the top. Okay, and so things get very complicated in a FinFET, which leads to all sorts of different stress interactions. But as with pre-FinFET, mechanical stressors are way more effective for PMOS in terms of how much you can boost hole mobility versus electron mobility. And so the beta ratios, which is the relative strength of the NMOS to the PMOS, is actually closer and closer to unity. And so basically, tricks that were to deal with a weak PMOS, such as pre-charge logic, etc., they're pretty much useless in FinFETs because you have equally strong PMOS and NMOS. In fact, actually, because of the asymmetry in BTs between PMOS and NMOS, you may find that actually there are conditions at very low supply voltage where the PMOS is actually stronger than the NMOS. That's how far we've come. Okay, as you might expect, the stress and therefore the mobility, which depends on the stress, it depends on the length of the active area, the width, the space between active areas. And so, bottom line is mechanical stressors has been a host of a lot of layout dependent effects that's gotten stronger and stronger, which means that the simulation gap between pre and post layout has gotten even stronger, or the discrepancy has gotten even worse. HighK metal gate. the key thing here is as we keep scaling the gate length shorter and shorter, there's less fin volume that the gate wraps around, which means that if you were to use implants to basically give you the different VT flavors, it's becoming less and less effective. You're getting back the random dopant fluctuation you fight hard to eliminate in fully depleted devices. And so basically in the most advanced nodes, the VT tuning is done exclusively through flat band voltage adjustments, which is basically through changing the metal gate composition or the HighK dipole, the use of HighK dipoles, okay? What I want to mention also is that the metal gate layer, which sets the work function, which comes in intimate contact, unfortunately, nature's not very kind to us. It gives us the right work function, which allows us to set the flat band voltage and therefore the VT correctly. However, because it's very resistive, basically the effective work function of the gate is influenced not just by the work function of the work function metal, but also of the metal fill, that lower resistance metal fill that you have, okay? And so this gives rise to basically very complex threshold voltage versus gate length behaviors, okay? One thing that hurts RF very dramatically, and also logic for that matter, is the fact that, you know, the gate resistance is also very bad in these scale nodes. And so basically non-quasi-static effects are increasingly prevalent. And lastly, because we have gone to a silicide last process I mentioned earlier, the fact that we have these silicides only at the bottom of the contact, not strapping the entire diffusion, it basically means that the source drain access resistance to the transistor is very high. Okay, so just a quick refresher on flat band voltage. I want to mention here, do not return to your prof everything you've learned about capacitance voltage characteristics. Basically, you know, VT is a sum of two terms in its most simplest form. It's a sum of this flat band voltage plus the change in gate to source voltage required to convert or to move the MOS capacitor state from a flat band state shown here to an inversion state where the inversion layer forms. Okay, so the flat band voltage is effectively the offset. It consists of a host of different terms. Most notably, it consists of a work function difference between the gate and the silicon surface side. Also fixed oxide charge at the silicon dioxide surface interface, which is becoming increasingly insignificant because increasing COX makes this term less relevant. But then you also have fixed charge in the dielectric that can also shift the VT. You can adjust the flat band voltage by adjusting the work function of the gate metal, but you can also induce dipoles into the HighK dielectric in order to adjust the VT as well. And the depth of this dipole and the charge density of the dipole can dictate how much you can adjust the threshold voltage. Okay. Okay. Now, as we keep getting to tighter and tighter contact to gate pitch, it's inevitable that it's going to be tougher and tougher to land diffusion and gate contacts without the diffusion contact shorting to the gate contact. In 28 nanometers and earlier nodes, we were used to basically having only one mask for doing the diffusion contact as well as the gate contact. But as we've moved on to these advanced nodes, life is not that pretty. Basically, what has been required to land contacts into this contact module, which is sometimes referred to as the middle end of the line module, is to basically have self-aligned diffusion contacts and gate contacts. So for instance, after we do our contact dielectric and polish, it's not uncommon to grow a protective gate dielectric cap, which allows us to basically incorporate a self-aligned contact, which if the self-aligned contact is misaligned, it will not short to the gate because there's a protective cap there. Furthermore, it's not uncommon that you would want to protect the self-aligned gate contact, or self-aligned diffusion contact with a dielectric cap, because then as you do subsequent, for instance, self-aligned gate contacts, you need to make sure that the self-aligned gate contact, if it's misaligned somehow, it's not going to inadvertently short to the diffusion contact. So this is extremely complicated, as you can imagine. It's not uncommon to have, what was one mask in 28 nanometers blow up to basically, more than a dozen masks to build the middle end of line. And you can see that there are more and more interfaces because you've got more and more vias and metal and so forth. The net result is the access resistance to the transistor has just gotten that much worse. Let's talk a little bit about self-aligned gate contact. What is it? The idea here is that, well, historically, we're used to landing the gate contact on the gate overhang, okay? Well, the problem with doing that is that you now are constrained to, you can't make the standard cell height too tight because this gate overhang restricts you from doing that. So if you can somehow land the gate contact directly on top of your gate, okay, on top of the active region without shorting to the source drain contacts or vias, then you can have a much more compact standard cell, reduces the height, reduces area, and furthermore, it reduces the non-quasi-static effects that happen due to the gate resistance, because now electrons have to travel a shorter distance to basically get to the active area. Okay. We have also incorporated another interesting design technology, co-optimization, to reduce the gate overhang. If you look here, you see that because of the nature of HighK metal gate being a replacement metal gate technology, we see some sidewall HighK metal gate, which takes up precious space. And if you can essentially go to a process modification where you essentially cut the gate after you do the HighK metal gate replacement metal gate process, you can substantially reduce the gate overhang, which in turn allows you to compact your standard cell height even more. Okay, another trick to compact to save area in standard cells would be to use what's called single diffusion breaks. The idea here is that you need a dummy gate to terminate the active area for the left device and the right device. Typically, there are different dummy gates, but this basically creates a lot of gate waste. So if you can somehow share the diffusion break with a single diffusion break, where you essentially isolate your left fin and your left device fin and your right device fin with a very aggressive isolation process, okay, you can essentially save a lot of logic, a lot of gate waste due to these dummy devices, dummy gates. Okay, one other trick you can play to make your transistors even or your logic gates even tighter is to depopulate fins. So if you depopulate fins, as you can see here, looking at a plot going from a 4-fin to a 3-fin to a 2-fin standard cell, and note that the number of NMOS and PMOS fins are the same because the beta ratio is essentially unity. You can see here that looking at power versus frequency, you can definitely get the highest frequency with the 4-fin device, but not by much, okay? And so if you actually went with a 3-fin, or better yet, a 2-fin device, you can see that for the same frequency, you can do this with a lot less power, okay? Or another way of saying it is, for the same power, you can, with a 2-fin, you can actually attain a much higher frequency. So these are the kinds of optimizations that are done to basically try to squeeze out, co-optimize the design with the process technology to basically get area benefit in standard cells, because you're not getting that raw area or raw feature shrink anymore, like historically was the case. Okay, I guess this was my first intended place to have a Q&A. Are there any Q&As we want to entertain at this point? Prativ, looks like you have a question.
Hello,
Go
sir.
ahead.
Hello.
Sir, I have a question related to the number of fins relationship versus the driving current capability. Suppose I want to use RCA structure, ripple carry adder structure, then what will be the relationship between number of fins and that driving capability?
That's an excellent question. So it turns out that you know.
Could you, Alvin?
Yeah.
Excuse me, Alvin. Could you repeat the question? I'm not sure I understood it.
Oh, sure. Yeah. So the question comes with like the driving, the FET current drive capability versus the number of fins.
Mm-hmm.
Okay. In other words, in a group, right? So that's actually an excellent question. In a regular planar device, generally speaking, you know, ignoring narrow width effect, you can essentially say that you know, the drive current scales linearly with the gate width, right? But in a FinFET, that's not the case. The FET drive current does not scale linearly with the number of fins. In fact, there's actually a point of diminishing return. The reason is when you have more and more fins in a wider OD, you actually end up having all sorts of complicated stress interactions where you actually get less drive current for groups of wider number of fins, larger number of fins versus having just one fin. So effectively, the current per fin actually drops as you increase the number of fins in a group. Okay, and it's a lot of it has to do with the complex interactions of the stresses and so forth. And also, you know, collecting the fins, the current from all these different fins requires diffusion contacts and so forth that are highly resistive. Okay.
All right, we have another question from Yasser.
I'm sorry?
Oh, Parthi, did that answer your question?
Sir, so basically, what are you saying that suppose I am taking a default device which is having, suppose I am taking P pin, which is having number of pins is equal to P FinFET, which is having number of pins is equal to 2, and also N FinFET, which is having number of pins is equal to 2.
Mm-hmm.
So should I proceed with default number of pins
for
better driving capability?
Well, all I'm saying is, for instance, like in these technologies, using two groups of 2 fins is going to do better than one group of 4 fins.
Okay, sir. Thank you very much, sir.
Mm-hmm.
Okay, so now we'll go with Yasser.
Yasser?
Yeah, I have a question. Yes, can you hear me?
Yes.
Great. Question on the techniques to adjust the threshold voltage. One was.
Oops, Yasser, I think you're muted.
Okay.
I'm sorry, Yasser.
Looks like...
I accidentally muted you. My apologies.
Okay.
Right. Go ahead.
Thank you. So the use of dipoles to adjust the threshold voltage, how does that affect flicker response?
That's an excellent question. You would expect that anything you do to kind of make the gate oxide more complicated is not going to do ideal things to the interface and therefore to the flicker noise characteristics, right? Okay. So, I mean, I have a slide that covers a little bit about flicker noise. Generally speaking, flicker noise has gotten a lot worse. Okay, in FinFET nodes. It is not a showstopper. You can deal with it by paying an area essentially, right? But you know, flicker noise is worse. You know, you can imagine that not only do you have like the ideal, you no longer have the ideal 100 normal anymore. You've got the sidewall, which is 110, right? And so you've got, you know, higher density of interface traps and things like that. So you know, that's not good news. Right, and so I can't speak to the specifics as to how much it's worse, but you don't expect it to work in the right direction, and so the foundries have to definitely do some things to recover from recover the 1/f noise from degrading too severely.
Okay, so
the other thing, one other point I want to add, right, is that the whole thing about using FinFET is conducive to low voltage operation, right? And so low voltage operation is going to naturally, for headroom issues, is going to squeeze the amount of overdrive you have on a transistor. And when transistors operate at lower overdrive, typically the flicker noise gets a lot worse.
Okay, so dipole itself is not the dominating factor of the flicker noise getting worse in FinFET.
It's hard for me to say. I can't really necessarily quantify that. It's not details that we're going to know a lot of. I mean, basically the foundries don't even tell us how they're exactly doing this. So they're not going to tell us which devices are correlated with to have certain dipoles and so forth. But it's a combination of dipoles as well as work function metal materials to give you different VTs. If I may add, the way dipoles are actually done is you typically pick a common material you would use is, for instance, lanthanum. You would deposit lanthanum on top of your gate oxide material, your HighK material, and then what happens is as you anneal the lanthanum in contact with the HighK dielectric, the lanthanum actually diffuses down and forms lanthanum oxide. And in the process, it creates a front that keeps penetrating below. And as that front penetrates down, it also pushes down a dipole layer, which creates that charge sheet to adjust your flat band voltage.
Okay, that makes sense.
Very interesting. Yeah. Okay.
Does that make sense?
Yes, sir. Did you have?
Yeah.
Does that make sense?
Yeah. It does, but it also creates lots of other questions I can follow up offline.
Okay.
Sure. Yeah. I think we need to move on, but thank you for the question, and it's a very interesting line. I'm glad you brought out how dipoles are done, because I was wondering that. So thank you for offering that, Alvin. But perhaps we should move on. Alvin, normally we go for typically an hour and a half. I'm happy to go for the full 2 hours that you were thinking of when you started. But anyway, I'm noticing.
I'm gonna go.
Some folks are dropping.
Unfortunately, but I thought I'd have to. But I mean,
Yeah, no, that's fine. I could have done a better job up front with that, so I apologize. But this is really, really interesting. So I'm just noting that I think the expectation of our normal attendance is that it's more like 90 minutes max, but it's okay, to go on
I mean,
longer than that. So
okay. I mean, would you guys like to stop now and then we can do it another week? Or
no, please continue on. This is excellent. I think Alvin, you're really bringing forward what's important in FinFET, and I want to we'll go through this whole presentation, please. Okay. I just wanted to note that you may notice that there's fewer attendees over time, but that's fine. It's to be expected, kind of, because we normally go not quite as long. However, it's recorded, and so folks can come back and listen to the portions that they missed. And so please, I think we should go ahead and do a nice job of what you wanted to do. So let's not worry so much about it.
So
okay.
So let me continue then. What I'm going to cover, now is kind of like the list of the gripe sessions of what FinFET brings to the table after we covered the technology. So one thing that you'll see FinFET being very common in these nodes is the use of stack FETs. Okay, so as I mentioned earlier, you've got a significant limitation in the maximum gate length that's allowed, and that's largely a CMP-induced restriction, because the replacement metal gate process does use CMP. Okay, when you use, for instance, like shorter channel devices, which is really the focus of the fab, if you basically pay attention to what the fab wants you to use for logic, right, you're going to be in better shape. And so using stacked transistors, stacked short channel transistors is way more process friendly than using longer gate devices. And you also get, in addition, with short channel devices, mobility boost in shorter gate length devices. And so when you have multi-finger transistors, you can actually run into this, what seems to be a counterintuitive result, where despite needing all the intermediate area for all these intermediate diffusion nodes, you might actually end up using less area for multi-finger devices, despite this area overhead, because you get the mobility boost in shorter gate length devices. Okay, and just to highlight, these intermediate diffusions don't come for free. At some, to an RF crowd, this is obviously important. At some frequency, these intermediate capacitances start to shunt away AC current, which means that if you, for instance, were to compare, say, a Lmax device of 240 nanometers versus a stack of Lmin devices, which achieves the same normalized R out, you can see that the R out basically starts to deteriorate at about 15-20% lower normalized frequency, simply because as AC current starts to shunt away through these parasitic capacitances and not go all the way through the transistor stack, then effectively it's going through a shorter channel length and therefore worse R out. Okay, let's talk a little bit about thick oxide IO FETs. So general purpose IOs still use a 1.8 volt swing, despite the core VDD aggressively going down. And so it's simply because these advanced node ICs still need to talk with peripheral ICs that are made in lower cost nodes. It is increasingly challenging to keep the 1.8 volt devices. Why? Because as you're making the fin pitch tighter, okay, it's making life more difficult to actually fill your replacement metal gate, HighK metal gate process. And with a thicker oxide, that's naturally more challenging. Furthermore, you need more complex level shifters to bridge a larger voltage gap between the a lower core supply voltage and 1.8 volt. So, if you can go to thinner IO oxides, such as say 1.2 volts, you can basically save a lot of power and area, but you do have to pay in gate leakage. However, that said, though, if you need to maintain 1.8 volt IOs with only 1.2 volt IO devices, you now need to do all the standard tricks with stacking transistors, building biases, more complicated level shifters, all that stuff. Okay, and when you run to work towards nanosheet integration, the space between the nanosheets, which is now oriented in the horizontal, you have to have nanosheets in the horizontal direction, it's going to be even tighter. And so this is going to be a much bigger pain. Using the ability of IO devices is going to be far, far more of a challenge in increasingly advanced nodes. Okay, now there are ways of solving this problem. The idea is not to go brute force against what the process technology is trying to steer you away from. So you can try to solve this problem of using IOs, for instance, using system, chipset or chiplet partitioning. And as you have more system ownership, you have more options on how you delegate, keeping away the high voltages from the advanced node dies. Passives, passives since 20 nanometers has migrated to a thin film precision resistor. Basically, poly resistors are no longer a thing that's available anymore, since due to the HighK metal gate integration. Inductors have largely remained unchanged in the upper back end of line. Capacitors, you are getting a little bit of higher capacitance density due to the lower back end of line having a tighter metal pitch. But then what I'm seeing more and more of is the metal space is increasingly the limiter in terms of interconnect TDDB reliability. And so basically, if you can't keep your metal lines really tightly spaced, you're not going to get a lot of capacitance density. So that's something to keep in mind. Diodes, bipolars, these are classic analog components you use for ESD, band gap references, things like that, thermal sensors. I mentioned the high series resistance. And so what it means is it's tougher and tougher to have a sweet spot where you have flat ideality for building band gaps and band gap references and thermal sensors. It's just not something that's scaling very graciously with advanced nodes. Because it's not scaling, it's becoming more and more expensive from node to node. And the rule of thumb, generally speaking, from one process node to the next, expect 40% increased cost. So if your area, if your density is not going up by 40%, then you're paying more for that for this component. Okay, interconnect resistance. Okay, so there's not much pretty to say about this. It is arguably the defining agony of doing FinFET era design. It is my my standard interview question. For someone who states that they've worked on FinFETs before, what's their biggest pain? If they don't say resistance, then they really haven't worked in FinFET nodes. Very simply, if you look at, for instance, some data that TSMC has shown, going from node to node, you can see that the capacitance has gotten a little bit worse, but it hasn't taken off exponentially like it has for the advanced FinFET nodes. Okay, and so because the series resistance is so bad, right? What it means is that the FET performance, especially when you're down to very, very low, very aggressive supply scaling, is going to be significantly compromised by source degeneration or access resistance on your transistor. Okay, gate resistance, I mentioned earlier, is a significant problem when you scale the gate length. This distributed RC is going to give rise to non-quasi-static effects, which is a big deal, obviously, in RF circuits. Okay, there are multiple ways to mitigate this. You can generally use shorter fins so that the distance to the contact is less. You can double side the contact, which is a standard trick to basically reduce your reduce your contact or gate resistance by about a factor of 4. Or if self-aligned gate contacts is available in your technology, take advantage of it. Okay, gate to contact capacitance is also another big deal. Here, I'm showing that you have basically this self-aligned contact forming essentially a very nice vertical parallel plate capacitor with the gate. Okay, and so what that means is that if you're talking about circuits that are very sensitive to gate to drain or gate to source coupling, such as say an LDO regulator, a low dropout regulator, or say a differential amplifier, you can end up for an ugly surprise. Flicker noise, I mentioned earlier, going from 20 nanometer planar to 16. The claim is 1/f noise is on par by the foundries, but in reality, what we have seen is it's a lot worse. Okay, and there are lots of different factors, obviously, affecting surface charge trapping, detrapping, and it gets worse at much lower gate overdrives, but it's not a showstopper. Okay, moving on to layout dependent effects. The stressors are much stronger and interact with the surrounding isolation a lot more, which means that the layout dependent effects are a lot stronger. You've got the classic length of OD, OD width, oxide space and gate pitch effects. Translates to basically a wider gap between pre and post layout simulation results. Okay, now the good news is these effects have been around since as early as 130 nanometers. And so, for instance, the LOD effect is captured. The models typically capture the change in mobility and the change in threshold voltage resulting from the change in stress. One stress layout dependent effect that was introduced in 16 and 14 nanometer is the gate cut stress effect. The idea here is that if you basically cut the gate, okay, for a bunch of, for a gate adjacent to a gate that is actually continuous, the presence of the gate cut actually disrupts the mechanical support of a continuous gate nearby and can actually impact the mobility, or essentially impact the stress of a nearby transistor. Qualcomm has shown some very nice device modeling where you can see that with a gate cut, you can see that the transistor stresses actually get modulated. Pretty freaky stuff, okay? But this is an old enough effect that starting in 16 and 14 nanometer, the mobility and VT adjustments due to this effect is well captured. For HighK metal gate, there are a host of other effects. One is the metal boundary effect. So with the metal boundary effect, the idea is that, well, you've got PMOS fins here, NMOS fins here, sharing a common gate. Now, clearly, with the HighK metal gate technology, you need a different work function metal over the PMOS versus over the NMOS. But it turns out that when you're building such a structure, there is going to be interdiffusion of work function metal between the two, cross-contamination of the work function metal. And when you've got cross-contamination of the work function metal, it also means you have cross-contamination in VT. And so if you've got devices, transistor or fins that are very close to this boundary, metal boundary, you're going to end up with VT shifts. Okay. There's also the density gradient effect. This is a particular headache for analog designers because we tend to have a habit of having mix and match of different gate lengths near each other. So the idea is when we've got different gate lengths due to the replacement metal gate process where you've got CMP dishing, you can actually have gate heights being different between short channel and long channel devices. The problem, as I mentioned earlier, is that the work function is influenced not just by the work function metal, but also by the amount, the work function and the height of the metal fill above. This is generally very difficult to capture in models because it's long range, as with all CMP effects. And so quite often you've got some pretty stringent density rules to limit this from being very severe. Talk a little bit about density and floor plan considerations. So typically in these nodes, there are many critical process steps, and they're also very sensitive to pattern density and loading. We've got now thousands of DRC rules, many very, very tough to pass. They're almost impossible even to understand what they mean. But the DRC's goal is to try to reduce all the unmodeled long-range systematic variation in transistors. And so because a lot of these DRCs are long-range, you generally don't find out you have a problem until you work your way up in the hierarchy of layout. And typically you need to do a significant amount of rework of smaller cells. Okay, floor planning also becomes more tedious and bloated. As I mentioned earlier, because you have higher series access resistance to the well, you need, generally speaking, more well taps and guard rings to prevent latch up concerns. And you also have a lot of DRCs that are about minimizing not just the range of densities, but also the density gradient from one region to an adjacent region. Okay, and so this is an example, for instance, of how we had to introduce wasteful transition regions where you have an area of very, very low gate density short channel devices to a region of high gate density long channel transistors. By having the decoupling capacitance beside these short channel devices would trigger a host of DRC violations, which requires you to space them apart and put essentially a transition region in between where you've got intermediate gate lengths to basically grade the gate density. Okay, so these are the kinds of things you have to deal with in these nodes. Okay, just a little bit about some of the process effects here. There are short-range process loading related variation where a local variation can modulate process parameters such as deposition rate, etch rates, things like that. they're very difficult to capture in the models. And so you have DRCs to pretty much constrain them from being out of control. So for instance, as an example here, if you were to do a deposition process for building a spacer, okay, if you've got an isolated spacer, typically you might find that if the process has a severe loading effect, you're going to get basically a thicker film deposited compared to when you've got dense features. Very analogous to, for instance, painting a smooth wall versus a very rough wall. You know, all the surface roughness in a rough wall will take a lot, you know, will take up a lot more paint. That idea. And so you can also run into epitaxy loading effects depending on the number of fins you have, etch loading effects where the etch depth depends on the spacing, the opening that you're trying to etch. All these effects are need to be controlled with DRC. You also have long range density effects. For instance, rapid thermal anneal. This is a nice example presented by Intel, where if you don't optimize your gate density and make everything uniform, when you do your rapid thermal anneal to activate your dopants, the surface reflectivity can be different due to the material density being different. And you can actually end up with a lot of process or temperature variation, which results in device variation. Of course, with long range density, CMP is another classic one, where if you've got variation in line space and line width, you can actually end up with significant variation in electrical characteristics due to just different amounts of dishing and erosion. Okay, now just a commentary about FinFET node models. FinFET models now are based on, they're all BSIM CMG, or for common multiple gate. This is in contrast to BSIM IMG, which is independent multiple gate that's used for instance, fully depleted SOI process technologies, where you've got the front gate and the back gate underneath the buried oxide. They're based on channel surface potential, which means less equation fitting. Okay. However, these models are still very much target based for the latest nodes. And so what it means is that there is an uncertainty and error bar associated with that. Okay. The backend models, you will find that there's basically only electrical information provided. There's very little to no physical stack up details that the foundry will share with you in fear of protecting their, of contamination or just basically leaks of their IP. And what we've also seen over the years is that with customer pressure pushing against the foundries to basically not have very conservative backend corner models. The corner models for the backend are increasingly less pessimistic, so that you can relax the time enclosure. You've got the usual reliability models, and just to highlight again, the foundries are extremely paranoid to protect their IP from competitors. Okay, and so most of the stuff, the nuts and bolts of what the PDKs offer are all encrypted. Very little physical information is available. Even, for instance, the gate length that you draw in layout is not the real gate length. And quite often you'll have all sorts of different masked booleans to conceal the process details of what the foundry is actually doing. Okay, this is just a note about what it's like to work in bleeding edge process development. The technology is going to be built using very speculative models at the onset with very high model uncertainty. As we have our contract to start our initial design, the foundries basically use that to start building test chips and start figuring out how to get to the model targets. Invariably, they'll miss the model targets, and so that will mean that new models will be released, which will then be used for updating a design. And then ideally, you end up with a silicon-based model, which has virtually no model uncertainty, which is used for the final design. This is wishful thinking. In reality, it never happens this way. In reality, we always end up using some silicon-influenced model to build our final design. Few words about pre to post layout simulation gaps. You just have to accept more iterations in each node, And so you need to factor in that because you have to iterate in your designs, it's never too late or never too early to start your layout. Okay. There are multiple sources of the layout delta. One is the layout dependent effects, basically what defaults you have in schematic. If they don't match what's in the layout extracted values, you'll get a source of delta. And also, more importantly, the parasitics due to the middle end of line and back end of line are not anticipated in the schematics. Okay, so you can estimate, do a pretty good job already in the pre-layout net list. What's already captured are the source drain contact resistance, which is a huge deal because source degeneration is a very big problem in this node, in these nodes. Gate resistance can be captured and gate contact capacitance can be captured. So because the layout is so heavily constrained due to all these really constraining DRC rules, basically the context of what the layout will already look like at schematic level is already increasingly known. So this allows you to estimate the parasitics more accurately. But if you can make the schematic more layout aware, that's going to reduce the gap a lot more. Okay, and so some examples how you might do this is if you can somehow back annotate the key parasitics into the schematic, as well as specify the FET schematic options that reduce, estimate, and reduce the gap in the layout dependent effect parameters and the parasitics, that will obviously help. So what are some of the design strategies of how to deal with the advanced nodes? So one, for instance, is to avoid mixing short and long channel as much as possible. Okay, the short channels are actually patterned using self-aligned spacer-based patterning. The long channels are actually patterned using a conventional second mask. Okay, if you mix and match, you're going to run into basically DRC violations with density gradients, things like that. And so an example here, if you were to have a simple current mirror with enabled devices here, you could do this by converting the short channel devices to all long channel. But then an even better thing for what the process wants is you can basically make the long channel devices, convert them into stacked FETs. And so this would be what the process would want. Okay, how might we mitigate middle end of line resistance? So for instance, this is a really big deal in, say, IO drivers when you want lots of current. Clock buffers, also very current hungry circuits. One way to do this, for instance, is to use double source layout. So the idea here is that normally, instead of having one shared contact for west and east going currents, you basically split this up and essentially have like, a duplicate contact. And by having a duplicate diffusion contact, basically you now have the left contact servicing the west going current and the right contact servicing the east going current. So you've paid an area, but in the process of doing this, you now have half the current flowing through each contact and therefore half the droop. So, you are paying in area, which results in also slightly higher capacitance, but quite often this is the preferred solution that gets you the overall reduced area because you get that much more drive current. Another thing you can also do is, may not seem like a big deal, but if you, for instance, extend the self-aligned contact here such that you can land an extra source drain via, because these source drain vias are so resistive, once again, you can reduce the IR droop in getting to access the transistor. So these are the kinds of things that may seem kind of counterintuitive based on what we're taught in basic school layout that are becoming increasingly critical if you want to build your circuits for maximum performance. The back end of line resistance, one way to deal with this is to basically layer promote. Okay, so for instance, if you've got a standard cell talking to another standard cell with a very long wire using a very low, very dense wire, but very resistive wire, you can do better by layer promoting to a lower resistance wire. You eat a little bit more source resistance or via resistance, but then your metal resistance gets substantially less. You can kind of compromise by creating what's called via pillars to reduce your via resistance even more. This helps you, But if you're doing this for standard cells, keep in mind that the via pillars are going to create a lot of blocks for routing tracks. Another thing that has become very prevalent in the advanced nodes is to use continuous OD or continuous active area. The idea here is that when you've got a short active region, okay, because of the way the stress is impacting on the surrounding isolation, and also the stress that is created from the source drain regions. If you've got a short OD, you can see that basically the stress and therefore the mobility versus position changes. Okay. However, if you've got a much longer OD, okay, basically the mobility starts to saturate. Okay. And after the mobility starts to saturate, you now have this stress plateau where basically the stress and therefore the mobility is now constant. And so this is a way of getting the best performance and matching, in particular for PMOS transistors. Okay. But the key thing here is, in order to do this, you need to make this OD continuous, and you need to pay a certain amount of dummy gate tax at each end to build up the stress plateau. Okay. Okay, moving along. Some other pointers. I mentioned earlier that resistors aren't scaling, and so it's getting more expensive in each node. Okay, and so 40% more expensive in each node, and so for every 2 nodes, each resistor is going to cost twice as much. Okay, so if you can somehow build circuit topologies that are resistorless wherever possible, for instance, having a fully resistorless TX controlled impedance driver, or for instance, using less CML and converting more to CMOS, that's going to help make your circuit design more area friendly. Okay, as I mentioned earlier, bipolars and diodes are not scaling. Okay, and so they're going to get more expensive, and they're going to be even more non-ideal. And so, you're paying a lot to continue to use all these different tricks. For instance, you're trying to build a band gap. There aren't many good alternatives. But if you were to use band gaps, using, for instance, like chopper stabilized offset cancellation, using dynamic element matching in your current mirrors, etc., you're paying a lot to deal with the non-idealities of the process. Okay, so clearly this has resulted in a lot of research interest in non-diode based alternatives. Self-heating, as I mentioned, is a reliability concern. It's really a reliability concern both for the devices as well as for the overlying metal. Okay, so the strategy to deal with self-heating, if you cannot stop the heat from generating, you have to come up with essentially ways to mitigate the self-heating by sinking the heat away to the surrounding substrate or metal. So you can insert dummies, use, for instance, well taps to essentially funnel the heat away. The tricks are pretty much common sense to a large extent, but it's really mitigation, not really a way to completely circumvent the problem. I want to talk a little bit about how we deal with target-based uncertainty. As I mentioned, we are, if you're using the most advanced nodes, you have to deal with the fact that the models have a large error bar. Okay, and the fact that in each new node, the process at tape out is increasingly more immature, which means that the error bar in the models is higher. And this is simply a direct reflection that we have more mass, longer cycle time, even though we get some relief from EUV. But the bottom line is, with a longer cycle time from start to finish, in a given 2-year period, for instance, to develop a process, there are just simply fewer cycles of silicon learning. Okay. Now, what happens is that well after tape out, there are process development areas that are still active, and specifically where the sensitive modules are, for instance, the HighK metal gate, replacement metal gate, tweaking to get the various VTs to land on target, source drain epi, middle end of line, where usually where the yield problems are, that tends to be a huge area of focus. We also have a lot of fancy constructs to save area, such as single diffusion breaks, the more process features you have, the more process development required to get things to yield and have enough process margin. So what it means is that we've got a lot of parameters that are very vulnerable to shift because they're uncertain, such as the transistor VTs, mobilities, and layout dependent effects. And to further complicate life, the fab is concentrating on the logic devices, not the long channel and the IO FETs. Okay, and so I've certainly lived my share of roller coaster rides dealing with process models being off for long channel and IO transistors. Okay, so how do we deal with this? You do need to design in some margin to account for uncertain models, but you can't overdo it. Otherwise, you're just going to give up too much PPA in exchange for a very robust design. One way of dealing with process uncertainty is to build what's referred to as, or build a template-based cells for analog circuits, for instance. And this is, basically trying to essentially mimic what has been done for digital standard cells for decades. So the idea here is that you have these analog cells that are technology aware, such that you can have faster design closure and productivity. And the idea is that you have layout considerations all baked into these analog cells, such as anticipating density concerns, using short channel stacks, predefining your routing tracks, somehow maybe include some middle end of line and lower back end of line so that you can assemble things better, layer promote to lower resistance metallization for interconnecting cells. So you see where it's going by construction, steering, creating superset P cells that basically enable the layout folks to basically do the right things by construction. Okay. You can also have in these analog cells schematic considerations to reduce the gap you're going to see between pre and post layout simulations. I mentioned, for instance, if you can anticipate layout dependent effects with, say, continuous OD placement, you can override the SA and SP parameters, and a host of different other things to basically increase the efficiency of your layout. Let's talk briefly now in closing what's ahead. Okay, so we'll cover some FinFET improvements and basically look beyond FinFETs. So here we are at 5 nanometers, and basically what I can say is it's been really tough after 4 generations of FinFETs. Okay, there is really no low-hanging fruit with each new node, and what you'll find is that the fab is paying a very high price in process complexity and with some really funky innovations to basically get very little incremental gain. So just to kind of give you an idea, for instance, a 5% improvement in ring oscillator frequency is a huge deal. Okay. When you look at the areas of development, no stone is left unturned. Basically, the fab is, basically you're trying to solve the problem by 1,000 cuts, trying to optimize the living hell out of every little detail in the transistor and back end in order to get that little bit of performance improvement. So what's next after the FinFET? So the problem with FinFET is that as we try to scale the FinFET gate length, it's ultimately going to suffer from poor short channel control. Okay, and simply because the leakage at the bottom of the fin, where the gate is not wrapping around, is where you're running into a difficult time turning off the transistor. Okay, so how do we fix this problem? Well, that's where we go to the gate all-around nanowires or nanosheets. Okay, and so we solve the problem by basically wrapping the gate around the channel. Okay, now what we can say is that nanowires, which is basically the limit of a nanosheet with a very narrow width, offers better short channel control naturally because the gate is much closer proximity sandwiching around the transistor channel, but nanosheets are going to offer better area scaling. So my expectation is nanowires will likely not see light of day and will migrate directly to nanosheets. And just for the record, different companies call them different things. Nanosheet is used, nanoslab is sometimes used, and nanoribbon is also used, but it's essentially the same technology. Okay, yeah. Let's talk a little bit about how we would migrate from FinFET to nanosheet. So in going from a FinFET to a nanosheet, we would have a finified, basically a finified active area, but then in going to a nanosheet, we now have the ability to adjust the width in a more continuous fashion now, like a planar device. So if you actually look at a nanosheet, you could almost think of it as a bunch of planar devices stacked on top of each other, right? Okay, and so when we go to a nanosheet, things look a little bit more complicated though. If you, for instance, look in the cut in the width direction, you see the different nanosheets and the gate wrapped around each one. In the channel length direction, things are a little bit more complicated. You see the gate wrapped around the various nanosheets, so the nanosheet is in green. Okay. The problem with the nanosheet structure though is that the source drain is going to basically have a very strong overlap with the gate, and that leads to a very, very severe capacitance, which you have to reduce by inserting these inner spacers in between. And so this is one of the key process challenges in realizing a nanosheet. Some other things to also note: in a nanosheet, we have basically tilted a fin down to its side like a planar device. And so with the current flowing mostly along the 100 surface, we are back to a point where the electrons love it, but the holes hate it. Okay, so what does that mean? Does that mean that our PMOSs need to be, wider than our NMOSs for the same drive strength? Quite possibly. Okay, I've talked about the inner spacers. The other thing also that's absolutely important to realize is that we have a parasitic planar device underneath here, and it's very critical that this planar device shuts off completely, because a planar device at these very short channel lengths is going to basically be completely a useless device that you cannot shut off. So you will need very, very high dose implants underneath to basically shut this parasitic device off. The other thing also to note is that in a nanosheet, you cannot just keep stacking these nanosheets indefinitely to get a lot of effective W per unit area, because the access resistance from the contacts down to the bottom most nanosheet will render the bottommost nanosheet almost useless, because the access resistance is so high. Okay, what happens beyond nanosheets? So this is where there's a lot of research being done on 2D or two-dimensional or one-dimensional materials. So the idea here is to have basically very, very thin channels. Okay, why do we need this? Simply because as we make the channels shorter and thinner and thinner, you can see here that the mobility of silicon abruptly falls off a cliff. Okay, so that's obviously not good. So there's a lot of research into what's referred to as TMDs, or transition metal dichalcogenides. Basically a transition metal grouped to two group 6 elements, such as sulfur and selenium. If you look at these guys here, these are two-dimensional materials. So the idea here is you would grow an atomically smooth single monolayer of this compound, and that actually has been shown to actually have much higher mobility for a much thinner channel. Okay, and just for those who are curious, if you are still changing your own engine oil, you might find that moly disulfide is actually one of the chemicals that's used for very, very good lubricant, good lubrication type motor oils. That might be kind of fun to know. For single dimensional materials, carbon nanotubes would be the obvious one that people are looking at. You can see carbon nanotubes definitely have much higher mobility, well into very, very small channel thicknesses. The challenge is the integration to actually grow it and actually contacting and making useful transistors in an integrated circuit. Okay, so with that said, thanks very much for bearing with me through this presentation. There's a very nice quote from Philip Wong from some years back. He gave at Hot Chips, where basically it's still clear that there's still room, even though things are getting tougher and tougher, but there's still room for device scaling and transistor density increase. It's still alive and well. It's not even sick. And when scaling at the node level or a single die level runs out of gas, there's already a lot of work looking at heterogeneous integration, stacking, 3D, all those kinds of things. Clearly, you can tell that when you're doing a SoC area scaling, it is not just feature size reduction anymore. It's driven largely by device innovation and, more importantly, by a lot of design technology co-optimization. FinFET area scaling, it clearly prioritizes logic and less so memory now, certainly not classic analog. What we are experiencing is that if you want to implement something with a little bit more performance or what have you, you need a ton of perspiration to get very incremental inspiration. With that said, if you understand and exploit the technology, for maximum power performance area benefit, and you can be in a much better position to, really get efficient design productivity. This is by understanding the technology nuances. With that said, I've got some references here listed that I've been, I invite you to look at, and Q&A.
Wow, thank you, Alvin. And I really appreciate all the references there. I've noticed that, I guess I had a question about your, your analog templates, right?
Yeah. Sorry, analog. What is
templates?
Analog.
You call them templates?
Oh yeah. The analog cells. Yeah.
Yeah, analog cell or template. Yeah, there was a slide on that. You showed various representative examples in there that speak to, like I think I'm seeing, stacked diff pairs. I'm seeing stacked M and P. But I'm going to take a look at this paper, number 47 here, but I think this is fascinating. And I guess I also heard of some of this. I think it might have been RFIC or maybe ISSCC. I think there was a paper maybe from Intel, like kind of doing a similar idea for even RF and millimeter wave kind of things, where you really have to optimize, right, the layout cell. So I'm trying to, I guess, in your role and in your experience, how is this going with designers? I mean, are they finding these acceptable, or do they tend to, want to kind of follow your lead and do their own? So how well is that working?
So that's an excellent question. Part of the problem, from my experience, and also, I see it in my own behaviors, right? As I've been working on the designs, analog and RF circuit designers, we're a pretty stubborn breed, and we're a stubborn breed who are very accustomed to having a lot of flexibility, right? And I won't go into details of what is quite stereotypical of what analog RF designers think of digital designers, but the very fact is it's the digital designers that rule the world, because all this process technology is all geared towards digital, right? And so the sooner analog and RF designers embrace constrained design, okay, figuring out ways to basically design, in particular, work in layout, right? To basically, like I say, just embrace what the process technology is wanting you to do, despite how crappy it may be, right? The sooner you're gonna be moving forward. Okay, and so what I see is with designing with constraints, it's not easy because we're not used to designing in constraints, the barrier to adopting these types of analog cells I've seen in the past has been largely psychological more than anything else, right? And there are a host of different techniques for improving analog design productivity. I'm sure folks in this crowd are very familiar with, for instance, the analog generator stuff that Professor Alon has been evangelizing from UC Berkeley, right? Okay, amongst his colleagues. There's a lot of potential ocean boiling stuff that is presented, but teaching analog circuit designers to basically codify their design flow in Python in a script is not something we're used to doing.
Right.
So in a similar way,
but if your feeling is that that's the direction to go, and you were referring to the Berkeley analog generator bag, I think, and then I think so. Did you go that route? Just out of curiosity, or did you go your own route?
I've definitely taken a peek into it and looked into it. I think there's a lot of promise. The challenge I still see is getting mass adoption across analog designers who are not used to doing this.
Yes.
It's almost better to actually have fresh outs, new college grads who are kind of uncontaminated, so to speak. Old way of doing
I gotcha. Okay.
I'm
gotcha.
Sorry.
Okay. No, I understand.
Yeah.
I understand. I follow. I don't know if my audio is a little poor. I apologize. Well, that's I really appreciate that. If there are any other questions, folks could raise their hand. Going once, twice. If not, Alvin, thank you so much. I really appreciate this, and to the folks who stuck around for the first hour and a half but had to drop off for whatever reason, they'll be able to pick up the last sections from recording. And again, I really appreciate you doing this, because as you said, you don't get many cycles of learning in FinFET, amongst the design community. And now, our members have a leg up when they encounter a FinFET design somewhere down the road, where they're going to avoid some pitfalls. And I really, really appreciate you sharing that wisdom with us.
Oh, sure. It's my pleasure. It's really not that, from the design perspective, there's a lot of challenges. Actually, a lot of it's basically parasitic management more than anything else, right? But in migrating from a planar node to a FinFET node, I mean, you do get discretized, quantized channel widths, for instance, and a whole lot of nasty rules. But it's kind of the same, and frankly, it's in the Foundry's best interest to kind of black box all the process details away from you as much as possible, right?
Right. That makes it challenging, because unless you have these insights into what the process wants you to do, like you say, versus what you did previous generations, the long channel, short channel thing is very striking on that. And a great example that is accessible. So yeah, sure. Again,
well, that's the difference.
Thank you very much.
Right?
I'm sorry?
That's the difference maker. I mean, understanding the technology.
Very good.
Yep.
All right. Well, I'm going to ask Tan to share the last few slides, and I think you're going to talk about next week's talk. Is that right? And do we have that?
You see my screen?
I do see your screen, but I think if you swapped the the displays, you'll get the right one being shown. You have the speaker's view being shown.
Okay.
Now, if you go up to display settings, go up to display settings at the top.
Okay. Let me try again.
Hello?
Can you see it now? Is it better or is it still not?
We can just move on. Yeah, just go on. That's
Okay.
fine. Okay.
So I
Backwards,
just
that's
got a
okay.
couple. Yeah. Sorry. Let's see here. Yes, I got a couple of administrative slides to review. One is a reminder that the MTT-SCV officer election is going on right now. Please vote at voting.v2.ieee.org. The last day to vote is 5 days away on the 22nd of November at midnight. That's Eastern Standard Time. Okay. And then the last slide has essentially is that IEEEs and its members inspire global community through highly cited publications, conferences, technology standards, and professionals and educational activities. The Microwave Theories and Techniques Society focus on the theory and application of radio frequency guided wave and wireless technologies. Please support us by becoming a member, and you can join the IEEE at www.ieee.org/membership, or you can join the MTTS at www.mtt.org/join-MTT-S-O. And please also follow us on LinkedIn at MTT-SCV. Thank you very much for joining. I don't have the information on next week's slides, but we'll socialize that out through emails and our normal channel.
Yeah, look for us on LinkedIn. I think we're having Wall Lang from Georgia Tech, if I'm not mistaken. So it's bound to be an excellent talk. Okay, thank you, everyone. I think with that, we'll go ahead and stop the recording and close the meeting. Until next month, folks. Bye for now.
Thanks a lot, Tom. Thanks a lot for this wonderful opportunity.
Oh, you're welcome, Alvin.